Cool. So I guess before we go into the actual talk, I want to give a brief introduction about myself. Like Bill mentioned, I was a software engineering intern at Google this past summer, and I was on two teams actually. I was part of the TensorFlow team and also the Kaggle team. And so I spent 50% of my time at one team and the other 50% at the other. So that was over the summer. During the school year, I'm a student. I'm currently an Eggleston Scholar at Columbia. I study biomedical engineering and computer science and do research on the side. So this talk is going to be about one of the notebooks that I've created during the time that I was an intern this past summer. So I hope you'll join me on this tutorial for creating romantic period art with TensorFlow. And so when I mean romantic period art, I mean art from the Romantic era, so like the 1800s by William Blake, etc. And before we get into the actual tutorial, we should probably start with understanding a little bit about the architecture. So what is a DCGAN? So there's a lot of letters, but in order to understand the DCGAN, we first have to understand a little bit about some other architectures first, because the DCGAN builds upon these other structures. So the first thing that we'll try to understand very conceptually is the neural net, then the convolutional neural net, which is the CNN, the generator, the discriminator, the GAN, the general adversarial network, and then the DCGAN. I do want to preface this presentation by saying that this tutorial and this workshop is supposed to be a high-level overview and a high-level understanding of generating art. It's not supposed to be a very like a conceptual and like mathematical, very heavy into stats and probability. So we will not be going over that for this talk, but if that's something that's interesting, I'm sure there's a lot of other workshops at AI Camp that goes over those topics as well. So to begin, let's talk about the neural net. So the neural net is the fundamental architecture for all deep learning, machine learning models. It's basically a bunch of nodes, and these nodes were initially inspired by the human brain neuron, although it has deviated quite far from the human brain cell. But basically you would have multiple layers. So you would have the input layer, and for us, since we're working with computer vision, our input layer will be an array of values for pixels for an image. Then comes various hidden layers, where you compute different things from the nodes to go to different nodes in the next layer and the next layer and the next layer until you go to the output layer. So between each layers, there's these arrows. And so these arrows are demonstrative of weights. And when you train the model, these weights adjust. So certain weights will become stronger, other weights will become weaker. And the way that this model is trained is through back propagation. So basically, you predict something with the neural net, and then it finds how much each weight contributed to the error or the loss of the model. And it will go in the opposite direction, it will reverse and adjust the weights accordingly so that the error is reduced. And that's how the model is basically trained. You would input usually a batch. So a batch is, for our case, would be a batch of 256 images. And yeah, so the output layer really depends on the model that you're working with. It can be a single node like this one in a binary classification, such as it's a dog or it's a cat, but you can also have multiple output nodes, for different multi-class classification, or for our case, for our generator, you would need obviously a lot more because you're creating an image and not just a single classification. So that's kind of the basic structure of the neural net. To build on top of that, we have the convolutional neural net, which basically is a neural net, but it has convolutional layers. So convolutional layers are very important for computer vision. And that is because when we see an image, we can understand that this is, a street, it's a pavement, but a computer doesn't know that. And the way that it can understand the images that's inputted is by learning different features. And so one kind of feature would be vertical edges, as you see on the top right. Another kind of feature would be horizontal edges. And these feature maps you get these feature maps through these convolutional neural nets convolutional layers, excuse me. And what they do is that you have a filter. The filter goes by each area of the image, and it outputs a value that corresponds with how strong a certain pattern exists. So for the top image, you would have a filter that outputs high values for places in the image that have vertical edges, and in the horizontal edge example that we see here, it'll output high values when it sees a part of the image that has a horizontal edge. And so if you add a lot of these feature maps together, like 64, 200, etc., you'll have a very, very, very large feature map for an image. And that's kind of what is generally used to do these machine learning, to learn and from these images. Okay, so the next thing we should probably talk about is a generator and a discriminator, because a generative adversarial network, which is what a GAN is made up of these two different models. So we have the generator. This image was from TensorFlow, so it has images of cats, although that is not the project objective that we have today. But basically, we can use this image to understand what a generator is. And a generator does what the name suggests it does. It generates images. It tries to create, in this example, cat images that look like real life cats. The discriminator discriminates. It determines if an image is real or if it's a fake. Generally, it's a binary classifier. You can get into more deeper or more complex structures where it's no longer a binary classifier, but for our purposes, we can understand it to be a 1, where the discriminator thinks that the image is real, it's a real image, and 0, it thinks that the image is generated by the generator. Excuse me. So how this works is that the generator and discriminator are trained against each other. And so the generator tries to create images that will fool the discriminator into thinking that they're real. And the discriminator tries to stay on top of the generator by being able to accurately classify the generated images and not be fooled by the generator. So that's a GAN. And then we go to the DCGAN, the next level up, when we add convolutional layers. Again, this is mostly, for a high level understanding of what these architecture is. We can get into different types of layers and what that means like later on, but this is basically the high level introduction to this architecture. So yeah, next we can go into more in depth about our tutorial. This tutorial is from my Kaggle notebook. So if you go over here and click on this link, you will go to this page where it has all of the information and all of the code blocks, along with explanations of what each code block is basically doing. This is just one of the many notebooks that are on my profile. So if you're interested in other examples, such as pneumonia classification or like COVID-19 versus pneumonia class activation mapping, there's like 20 other notebooks on here if you're interested. But yes, since that notebook takes a long time to run because it is a computer vision model, I can't do a live demo for the sake of this presentation because it will take over 30 minutes and we don't want that. But you can always run it live from the Kaggle website as well. But we'll be going over the main points of that notebook in this tutorial. Okay, so before we actually get into the code, we want to talk about our plan of attack. What do we want to do and how do we want to do what we want to do? Obviously, the first part, what we want to do is the identifying the problem. And for our example, we want to generate romantic era art. That's our problem. And in order to do that, we have to find a data set. So we can't do anything without data for machine learning models because we need data for that. And Kaggle has a lot of data sets, and I might be biased because I was an intern on the team, but they have a lot of public data sets for you to use if you're interested in experimenting with different models and learning more about ML, deep learning, or computer vision. And after you find a data set, you will set up your environment, what language you want to use, the packages that you want to use, load in the data correctly, and pre-process that data. This is one of the most important steps. A lot of people who are in machine learning really highlight the need to data clean. and to normalize data. And so this part of data feature extraction, etc., is a very big part, because no matter how great your model is, if your data is not that great, your model is not going to do that well either. And then we want to visualize your input to make sure that we're doing everything correctly, that we're pre-processing it correctly, the normalized images are coming out well. Then we want to build our generator, build our discriminator, train the GAN, and then visualize the outputs. It would be very nice if you can just say that we finished after. In many situations, you do have to go back and tune your hyperparameters. You have to change the number of epochs that you're training your model on, or maybe the loss function, or find new data if your data is kind of bad. But for our sake, we'll just say that's finished because we already went through that process beforehand. Before I continue, I want to ask if there are any questions. It seems that the Q&A is empty, so I will the chat. Okay, so yeah, it seems that it is empty, so I will continue. But if you do have any questions, please feel free to type in the chat or in the Q&A box as well. Okay, so again, I mentioned that I am biased with Kaggle because I work there, but I did find a great data set on there as well. It had data from the Cubism period, from Expressionism period, and Romanticism period. For our sake, we'll be looking at solely the Romantic art, but there are other data sets, not including this one, but other art data sets if you're interested in it, or medical data sets, or data sets of any nature that you might want to look for. Yeah, so it seems that there's a question. Can these be done on MacBook Pro? Do we need to do it on the cloud? Oh, so Kaggle is free for everyone. You can use it as long as you have internet. Doesn't matter. Doesn't matter what kind of computer you have. You don't need the cloud. If you have a Kaggle account, Kaggle has an API that lets you connect to like a public Google Cloud server thing, which I'll go into later. But yes, you can also, if you do have like a Google Cloud storage unit or project or whatever that you do want to use, you can hook it up to your Kaggle account as well if that's something that you're interested in. But yes, you do not need a MacBook Pro or cloud, Google Cloud. When training GANs, when do we decide that our generator is good enough? Okay, so I'll address this question a little bit later on in this presentation. Okay, so that's the first step, find a data set. Next one is setup. This is kind of boring, but it's a very necessary part of building your model. You need to make sure you have the right environment. A lot of people use Python. I guess that's just like the general convention for machine learning now. But you can also use R if that's something that you're interested in, and other languages as well. Obviously, because we're using TensorFlow, we'll be importing TensorFlow, and I'll be using Keras because Keras makes a lot of things very easy. It's difficult to do really complex things with Keras just because it is more of a high-level API, but it does make a lot of things simpler for us, especially in more basic models such as this one. I'll be using TensorFlow.Keras instead of multi-backend Keras just because it's better integrated with TensorFlow. And we want to use Kaggle datasets, which is why we import Kaggle, the Kaggle API. And we want to visualize our images, so we'll import PIL as well. Okay, this has been answered live. Is it possible to mix Keras APIs and regular TF APIs? Yes, it is. You can just use TF.image. Whatever if you want to do that, and then you can use TF.Keras for another part of your code. You can use both interchangeably throughout your code whenever and wherever you want it to do. So that's that. Is there any package in TensorFlow to support reinforcement learning algorithms? There are. If you also go to the Keras.io website, they have tutorials for reinforcement learning. I am not that involved, like I have not had too much experience in that. So, but I do know that Keras has tutorials and workshops if you're interested in, and TensorFlow has packages to support those learning algorithms. And can you generate a 3D painting from a 2D painting or 3D to 3D? That's not the topic of this workshop, but it's definitely possible. I won't be covering that in this tutorial today though, but yes. Okay, all right, cool. Next step is to load the data. So on Kaggle, you can easily use like TPUs and GPUs. For those who are not familiar, it will let you do like distribution so that you can save time. It'll be a lot more efficient when you train your model. There are tutorials on my Kaggle profile that do cover how to use TPUs. This one is not one of them, but if you do want to use TPUs, as of now, you can't use your local directory. You can't use your local directory. You have to use like a cloud directory, but that's okay if you're on Kaggle, because for all of the Kaggle public data sets, they provide you with a GCS, a Google Cloud Storage path that you can use, which will let you train on a TPU if you so choose to do. But this one, I use a GCS path, but I do train on a GPU, but that is something that I did want to mention in case people are interested in learning about df.distribute and how to use TPUs. So the first step is to load in the data. Because we're going to be using romanticism R, we'll bring that in. And this is not a classification, like this is not a classifier, this is not an image classifier. And because of that, we don't need to have a separate test data set or a validation data set. We just need a bunch of romantic art that we can train our model on. And so I'm just going to extend the file names to include the test set as well, so we can have just one holistic set instead of having multiple smaller sets that we do not need. We'll convert this list of file names into a data set. And so if you print out what each element in this data set looks like, it's basically a file path to the image. The B just stands for bytes because it is a TensorFlow string, it's in byte format, but yes, this is what is in the data set. How does compute affect the performance of assistant? Could you clarify that? I think someone asked what assistant are you referring to? I would like to know that as well. So I'll go back into that question once that is up. Okay, next up is to pre-process data. This is very, very important. And you also want to make sure that you're pre-processing data correctly and for the model that you're using. So for a lot of classification problems in computer vision, you're going to be normalizing from 0 to 1. And before we talk about normalization, we should first talk about the normal like data structure that the files come in. So images, when you just like import them and like decode the JPEG file, you will get an array, a matrix. And if it's a grayscale, it'll just be one matrix with, that's the size of your image. So if you have a 112 by 112 image, it'll be a 112 by 112 matrix. And each point in that matrix is a value from 0 to 255 that denotes the value, the color value for that pixel. If you have a colored image, you will have a red layer with the red values, another layer with the green values, and another layer with the blue values. And so it'll be a 112 by 112 by 3 matrix if your image is 112 by 112. And so as I mentioned before, for normal computer vision like classification, you want to normalize it to 0 and 1, but for generative models, it's convention to normalize it to -1 and 1, and so that's what we're going to do here. We first cast the image to a float 32. It's originally in uint 8, that's how like images come in, but we want to change it into float 32, especially if you're going to use distribute, because distribute only like takes in certain data types because of the way that it distributes the work. So in order to change 0 to 255 to -1 and 1, you would subtract 100, or you would divide by 127.5, so you get a value between 0 and 2. Then after you, after you get a value between 0 and 2, you subtract 1 to get -1 to 1. Yes, and then decoding images. So JPEG, when you like first like get it, is just a string of values, and it's really hard to understand what it means. You would need to decode it, and the tf.image function, oops, let me go back. tf.image function.decode JPEG does that for you, so it converts that JPEG format into a tensor that's 112 by 112 by 3, which is what we needed for this. This is an example of using, TensorFlow API with TensorFlow Keras API. You can use them interchangeably. We're not doing like special functions that make sure that it's only using TensorFlow or TensorFlow Keras. You can use whatever, whenever you need it to do. After you decode the image, you would want to normalize it using our normalize function that we already defined. And why do I decide by 127.5 instead of 128? Well, because the values are from 0 to 255, so 255 divided by 2 is 127.5. Yeah, and then just in case that the images are not, are not in the correct format that we want it to be, we'll resize it just so that it'll always be the same format when we input it into our model. So next comes the actual processing part. You would read the file. And that file path is determined by this output because we have that in our data set here. Decode the image as we defined earlier, and then we're going to convert the image to grayscale. So the reason why I convert image to grayscale is especially for style, like DCGANs are kind of like limited in what it can do. And so I didn't want the images to be too complex. If you have a complex image plus you have colors, it's too much information for the machine to learn. And so I just converted the image to grayscale so that there's less information that the model has to learn. You definitely don't have to do this, but it can lead to like better results if you do. We also want to change the dimensions of it into like a 4-dimensional array because that's what the model expects. And we'll process the path, we'll cache it just to save space, and then batch it with 256 images for a trained data set. So every time you call the trained data set, you will get a batch of 256 images that are 112 by 112 pixels and only one layer because it is now grayscale. Okay, next step is to visualize our input. We want to show the batch, make sure that we have like the images are normalized correctly, that we're not getting black images or white images or like weird colored images, that we have, the right images. And this is the function to define it. We have a PLT figure to plot multiple images. And then so for each subplot, we'll place the image there. And because it is grayscale, we do that. And then you get our data set. So this data set has now been normalized. It has now been changed to 112 by 112 for the size. And we see that for romantic period art, there's a lot of heads, there's a lot of portraits, which is probably the style back then because they didn't have photos or it was less accessible. And so this is the data set that we initially had after pre-processed. Next is building a generator. And so this is not the entire code for the generator model because it's very long. It will not fit on this slide, but the entire code is on that Kaggle notebook that I mentioned earlier. At the very end of the presentation, I can go back to the URL slide if you're interested in checking that out. But the reason why I don't include it is because the code is very repetitive. So you have your sequential layer because we're using a Keras sequential model. And you start off with the noise dimension. That's just, a random value that you use to start off with. And then you reshape it into a 7x7 image with 1024 feature maps. Okay, and then we'll use this very important layer, this conv2d transpose. Conv2d transpose is basically the opposite of a convolutional layer that I talked about in the beginning of the presentation. You can just think of it as a deconvolutional layer. That's another name for it as well. But we're going to use this to upsample our image. So we're starting out with 7x7, a 7x7 image. And when you repeat these 4 lines of code and change the strice to 2, then it will increase the size to 14 by 14. And then this value over here, 512, you will also change that as well because you wanted the feature map to like shrink. And so instead of having 1024 or 500 features, you wanted to go back to 1 because that's what the only layer that we had in our inputs that we had. So if you repeat these 4 lines of code, use batch normalization and make ReLU, you'll go from a 7x7 to a 14x14, and then it'll go up and up and up and up until 112x112. And that's your generated image. And before we train our generator, it's basically noise. And this is what we expect because it's not trained yet. We didn't input our data. It doesn't know what to look for. And so before we train it, this is the output of the generator, basically all noise. The other part of that is our discriminator. And so the architecture for the discriminator is basically a mirror reflection of the generator. So you start out with a 112x112, and instead of going up, you go down to a single node. A single node classifies it as, yes, this is a real image, or no, this is a generated image. And that's how the discriminator predicts the value of the image. For this one, I also didn't repeat, I didn't also include the entire code as well because it is repetitive and because you want the code to be visible. But basically, you would repeat these 3 layers, and instead of, and it would increase the feature map. So from 64, it'll go all the way up to, discriminator, and it'll go down. Sorry, my bad. It'll go down, and so until it becomes a dense layer with a single node. Okay, so training our model. Because this is not just a simple, deep, multi-layer neural net, we have to identify what our loss functions are gonna be. And we do that by defining our functions here. We have 2 losses. We have the discriminator loss, and we also have the generator loss. So the discriminator loss, what it does, there's 2 parts to discriminator loss. You want the discriminator to correctly identify real images, and you also want it to correctly identify fake or generated images. And so, the cross entropy, how you can understand it is that it's basically comparing this value to this value. So real output would be the output of like the real images, like the real romantic images, and it will be run through the discriminator, and you'll have a value of predictions of what the discriminator thought those images were. Ideally, we want it to be all ones, right? Because it's real images. And so you compare this to an array of all ones, a tensor of all ones, because that's what we want it to be. And if it's not all ones, then it would increase the loss, which is why we get the real loss here. Cross entropy does that thing for us. Fake loss is the opposite. Fake output is the output of the discriminator. And we want this to be 0, right? Because they're generated images, they should be 0. And so we compare that to a tensor of all zeros, and that is our fake loss. And we add those 2 to get our total loss, and then it returns our total loss here. Generator loss, what that does is that we want to confuse the discriminator. We want the generator to make the discriminator think it created real images and not generated images. So you have a fake output, you compare that to ones because that's what the generator wants it to be, and wants it to be ones, like predicted as real instead of fake. And that's the loss function for the generator as well. Okay, so now we have our custom training loop. Basically, it does exactly what I talked about in the previous slide. It generates images. It has a real output by by inputting into the discriminator real images, and it also inputs into the discriminator generated images, which is the fake output. You get the generator loss through a function defined earlier, and a discriminator loss by that function as well. So after you get these values, by using tf.gradient tape, you will run it on the gradient tape to adjust the variables based on the loss functions that you defined earlier. And then you would just train it with a number of epochs that you want. You can determine that through, I guess, trial and error, and it will output. Oh, you also want to save the images just in case, something goes wrong, your thing crashes or runs out of memory, something happens, you don't want all that time to be wasted. So what is gradient tape? Yeah, so I can talk about that a little bit. So I mentioned earlier that for like neural nets, it trains using like backpropagation. So basically what it does is that the gradient tape stores all the calculations made by the neural net, and then it does like, and then it finds the gradient, so like how much it has to change in order to reduce the error for each weight. And so the gradient tape is like the data structure in TensorFlow that stores all those calculations for you. And so it's needed to train the model basically to do backpropagation to adjust the weights needed. So that is what gradient tape is. You have your custom training loop. And then you just train the model with the number of epochs. I say epochs here because I don't like hard coding my variables because that's generally good practice. And so I have my epochs like instantiated earlier, and this is what you get. So obviously it doesn't look like the images that we got in the very beginning. And that is because DCGANs and generally it's used for more easier or more simpler types of data sets like MNIST. So MNIST is like a data set of handwritten digits from 0 to 9. Obviously that's a lot more simpler than, portraits or landscapes or paintings in general. And so it's harder for the machine to pick up those kind of more complex features. But we do see that it has. You can see the painting strokes that it has. It's a bit more blurred. You can also see, like a head and a body format, which makes sense because in our data set, we had so many portraits. That's what I picked up on. Something that might be a little bit more interesting and will lead to better results is if you have an input data set of just like portraits or just rivers or just of like one element instead of having like an era. I think that's a bit too difficult for it to pick up on. But yeah, this has been my tutorial workshop on creating generative art creating romantic art. And how much time did it take? I guess we can open up the questions. There has been questions throughout, but how much time did it take? So it took like a day to train, so not too long, I would say. And it was all on Kaggle too. It was not on my local computer. I used their GPU, and I was within the time constraints of that Kaggle has for their notebooks. Yeah, are there any other questions? Hyperparameter optimization. Yeah, so I didn't use Keras tuner for this notebook, but there is a new feature in TensorFlow Keras called Keras tuner, and basically it tunes your hyperparameters for you. I'm not sure how well it will work for a generative model, but it does work really well for classification. And that what you would do is there's a tutorial on the TensorFlow website, but basically you input like the range of values you want the hyperparameter to be, and then Keras tuner will just like go really quickly over those over that range and determine what's the best hyperparameter for you and just input it into that model. That's something you can use for hyperparameter optimization if you want something that's a bit more quick and efficient and requires less understanding, I guess, of CS literature. How hard would this be able to work on other forms of art like cartoon art? I don't think it'll be that hard, honestly. If you just want to use the same architecture that I used, you'd only have to change the data set and make sure that it's formatted correctly in the way that, the model wants it, 112 by 112 grayscale. And so it would not be that difficult. You would just have to pre-process the data on your own. But I would be very interested to see how that comes out. I think that would be a super cool kind of extension of this notebook. Would you recommend Kaggle over Google Colab for prototyping, working with GPUs and TPUs? So it really just depends. I like using Kaggle for like experimentation because of the public data sets that are available. If you're just going to be using local data sets or data sets from your drive, using Google Colab will be easier. You can also use Jupyter notebooks. There's a lot of different notebook platforms you can use to build TensorFlow models, so it does not have to be Kaggle. I just talk about it a lot just because this is where my project is. I'll go to that link also as well in case you guys are interested. And yes, so yes, it doesn't have to be Kaggle. But Kaggle does make it easy for GPUs and TPUs. Also, Google Colab as well. Jupyter Notebooks, it might be a little bit more difficult to use TPUs. When training GANs, when do we decide that our generator is good enough? So I guess in the beginning, so our generator is horrible, right? Because it's not trained, so it's all noise. And that's up to you. That's like the threshold that you want to do. So for me, this is, for fun. And this is, I guess, a more fun experiment. So even though the images didn't look like faces, I was still pleased with the output of that image. If you're doing something that requires more rigorous, like a more rigorous, I guess, like it needs to be specifically one type of image and it has to look a certain way, that's something that you would have to determine for yourself. But it is trained against a discriminator. So if your generator isn't working as well, maybe you should check into the architecture of your discriminator to make sure that's working like you want it to work. Yeah, so I think all of these talks will be on the website and on YouTube. So if you did miss something, they will be on there as well. Can DCGANs be used to extend the image? That I don't think so. I don't think you can use DCGANs to extend the image. I may be wrong on that, but I'm pretty sure you want to use this specific architecture for generating it from scratch. But there are other things. Also, if you're interested in like art, like style transfer for art, there's neural style transfer as well, and not just like DCGANs. Neural style transfer, there's a notebook on that on Kaggle as well, but also on the TensorFlow and Keras website if you're interested in that architecture. It's a bit different from this, but it works really well with style transfer if you're interested. Do you participate in Kaggle competitions? I have not really participated. I've created tutorial notebooks for them for certain competitions that beginners can use if they don't really know how to get started for competitions. I create notebooks for them and create a tutorial, and that's something that I've done over the summer as well. I've not participated in Kaggle competitions completely yet, so yeah. What about DCGANs to detect deepfakes? Oh, so DCGANs aren't used for classification or detecting anything, it's just generating. So if you want to detect deepfakes, maybe a classifier would be a better architecture style for that one than a generative model. And how can we use this for our own art? How much art pieces do you need? That's a great question. So this data set that I used was 300. But do keep in mind, let's say your art picture, like your art is like very big images, you can also cut it up. So like, let's say you can cut it up into 4. So if you have like 100 big art pieces, you can have 400 in your data set by just cutting it up into different portions if you're not worried about how that will affect your data. So this one only used 300, so not too much. Not too much. You can also like include data sets that you think is like good or like a good match with your own style of art. Any good course you can recommend to learn GAN? I would just say right now, experimentation. I used the book Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow to learn over the summer. But that's a good textbook that I thought was really helpful, especially for applied machine learning. I'm not really for like the stats and the mathematical basis of it, but for applied learning, it's very helpful. Right, thank you.
Great. I think we are out of time already. Thanks, Amy, for the presentations, for tutorials, and also a lot of questions. These are really great sessions to understand, to learn about the GAN.
All right, awesome. Well, thank you for having me.